I have been working at Pinterest for over 3 years now, and I've been working on the home feed ranking team, where I research and developing machine learning models and features. And our goal was to increase Pinterest user engagement as much as possible. So over these years, the models we launched and the features we added have increased Pinterest user engagement multifolds, which has been a key contributor to Pinterest's continued success. And without any further ado, let me share with you how we do that using machine learning and related techniques. Here is a little bit of introduction to Pinterest. So we are a company founded in 2009, and currently we have about 1,200 plus employees, and the company is valued at 12 billion USD. I hope more than that, but we recently announced that we now have more than 200 million monthly active users. So MAU is one of the most important metrics tracked by any internet companies nowadays. We view Pinterest as a personalized catalog of ideas. And on the website, the basic unit of information is a pin or a picture. And we have a few main sources of the pins. So for example, a user can take a photo and upload the photo to our website, and that becomes a pin. And the user can browse the internet, and when the user sees something really interesting and like to save, the user can save this picture or pin onto Pinterest, and that also becomes a source of our pins. And again, like when the user uses Pinterest and browse for new content, the user may encounter something that is surprising to him or her and would like to save that information to his or her own board. And that is like the content we get from browsing Pinterest. And every single pin is saved to one of the user's personal boards for categorization. So for example, a user may have an animal board where a lot of animal pins can be saved onto, and the same user may have a history board where historical pins can be categorized together. So on Pinterest, all these pins are presented in a user-friendly waterfall model. When a user logs onto Pinterest, the user can scroll down the screen to browse an endless stream of interest pins. And for every single pin, the user can take a set of different actions, like, for example, doing nothing, or repin or save the pin, or click through the pin to the third-party website. Or a user can also try to hide the pin if the user finds the pin is not relevant to the interest currently at hand. And we also offer some social interaction options for the users as well. For example, a user may choose to follow other users or other users' boards. If that is the case, then any new pins that are saved by the other users or saved onto those boards would become candidate pins that we would show to the user that are following the other parties. So currently, today, we have 4 major products, namely personalized home feed, search, related pins, and ads. In total, we are showing more than 10 billion pins to users globally every single day. And I'm particularly proud of this number because this is actually more than the size of population on the planet. So on average, every single human being is seeing at least one Pinterest pin every day, on average. So here are examples of our main products. The top left one is the personalized home feed. Here, all these pins are generated using recommendation algorithms or machine learning models. The user doesn't need to do anything extra, we don't require any extra effort from the users to be able to generate this homepage. And these recommendations are based on a user's historical interactions on pins that the user have seen on Pinterest. The top right one is search. This is a mature product that I believe many other companies would have similar search engines. So here we have a search box where when the user types in a query, a bunch of related pins to that query would be displayed in order of relevance. Here we also, unlike many other of our competitors, our search engine heavily uses personal information, meaning we don't just use query information to decide what is the related pins, but also take into the user information into our consideration. So the bottom product is called related pins. This is when a user browses Pinterest and click on any one of these pins. The user will be taken into a page that will display a lot more other pins that are related to this particular pin. So some of you may be asking, I mentioned 4 products, so why we only have 3 here, and where is the ad product? Actually, the ads are all embedded in these main products, And the goal of an ads product is for us is, of course, to generate revenue for the company. But at the same time, we really emphasize on the relevance of the ads product. So we want to provide a seamless experience for the user, and we hope that the users will find the ads very relevant. So as you can see, in these cases, like I have highlighted 3 ads embedded in the product, and I think they are more or less like kind of seamless, and the ads here are not very intrusive. That is one of our main goals for the ads product. Okay, so for today, I want to focus on personalized home feed because after a while, we'll see why it's the most important product from Pinterest. About 70% of daily active users are actually using home feed, and about 65% of repinners would save pins from our home feed. And 40% of total repin volume comes from home feed. And also a large portion of ads revenue is generated on home feeds. So I think it's not from any kind of truth that home feed currently is like the most important portion of our site, both for the users and for the company's revenue as well. Okay, and in addition, home feed is the first product powered by machine learning that makes it really relevant to this data conference here. And the core problem we have at home feed in terms of machine learning is trying to predict, quantify the relevance between a user and a pin. And the models would predict the relevance of more than 200 billion user pin pairs every single day nowadays, purely from home feed. So that number alone makes this really a big data problem that we are facing every day. And from various online A/B experiments, we have seen that the quality of the relevance prediction, by the home feed ranking models directly affect how engaging our users are on our website. So this machine learning problem, is usually core to the success of the company as well. Here, let me try to formalize our problem a little bit more. So our problem is a user pin relevance prediction problem, and we want to use a feature vector consisting of user features, pin features, and user pin interaction features to predict for every single user what pins we would like to show to the user in home feed among these billions of pins on the website to maximize user engagement. And user engagement is measured by whether the user repins on pin or clicks through the pin on the website, and whether the user comes back to Pinterest regularly. And we model this as a binary classification problem used in a ranking context. So every single training instance is from one historical interaction log between when the user is using Pinterest. And we generate a feature vector, which is various numerical variables that describe the particular interaction. And the prediction label, the ground truth, is a binary 0 to 1. 0 means the user has seen this particular pin, but the user didn't take any action, like just let it go. And 1 means the user has either repinned, meaning saved, or clicked through the pin. So we have some very confident positive interactions from this user about this pin. So now let's look at some examples of this home feed session. The left-hand side is an example home feed session for a particular user. As you can see, the user has basically has viewed this many like 10 plus pins, and the user decided to save or click through on the pins labeled with a green tick, and the user didn't interact with any of these pins labeled with a red cross. So in our offline training data generation, what we do is we will take the red cross pins as the negative examples because there was no positive interaction, and we'll take all these green tick ones as positive training instances. So as you can see, we collect this set of data from hundreds of millions of different users, and we can train an offline model. And when the model is completely trained, we use this model to predict for new online interactions. So for example, when we have 2 pins on the right-hand side, those are both candidates we want to show to a particular user. Through our model, we see that, okay, the top pin scores a higher relevance score according to the model than the bottom pin. What happens is in the generated home feed, we will show the top pin like higher up than the bottom pin. So trying to maximize user engagement. Okay, so here is a simplified version of our home feed system diagram. As similar to many other recommendation systems in the industry, we have 3 main stages, namely candidate generation, ranking model stage, and content blending. In candidate generation stage, the goal is to try to make the sets of pins we want to consider smaller. So if you imagine Pinterest, we have we have tens of billions of pins that we can show to any user, and the number is growing very fast. And the first candidate generation stage is trying to reduce the problem size from the billions to maybe only a few thousand, so that we can fully rank using the second stage. The way we do it is through a few different sources. So I described how follow user and boards work, and any pins that save to this follow boards or like by those follow users will become candidate pins. And also we have followed interests. Those are when a new user signs up on Pinterest, we ask the user to select some of the, I think from a list of 100 interests, what the user would like to see, because at that time, we don't have any information about this user. It's a very difficult code start problem for us. And once the user has selected these pins, we would populate content from those particular interests. And more importantly, we have this thing called Pick for You, and that is a recommendation engine in itself. So basically, we don't use any explicitly follow actions in the Pick for You source. We basically look at the co-occurrence of some pin board. Generally, Pick for You uses either collaborative filtering and random walk to decide what are the potential candidates we want to consider to rank for this particular user. And once we have generated thousands of these candidates for a single user, we pass all these pins to a second stage, which is a machine learning ranking model stage, in where we predict the relevance from all these user pin tuples, and then we rank this total order of all the pins for a single user and pass them to a content blending stage. The content blending stage is a post-processing stage that is relatively simpler, in which we add some business logic, such as in addition to maximizing relevance, I also want to ensure variety. I also want to ensure the pin freshness in our final home feed. So basically, it minorly adjusts some of the final ranking orders of the home feed pins, and then before display to the user. So these three stages are the main components in our recommendation system. And all the three stages are generated online in real time nowadays. So today, let's focus on the second stage. I think it's most exciting personally, and I will talk about the evolution of our models over the past few years. So here is the overview of what happened at Pinterest for home feed ranking. As you can see, we have made three major model changes over the years, from no relevance prediction model to a linear model in 2014 to 15, and then to gradient boosted decision trees model last year, and then finally moved to deep neural model this year. So let's do some basically prehistory talk here. So before 2013, and we have no relevance prediction model. All the pins come to Pinterest are shown to a user on a first come, first serve basis. So as long as we have the fresh pin, we show to a user. And as you can see, there's no relevance enforced at the final home feed ranking, so the experience was not really ideal at that time. But it was a simple system, and we were able to solve it very fast, and that helped with our user growth in the initial stage. So in 2014-15, we actually launched logistic regression and SVM rank with a linear kernel as our production ranking model. So as you can see, in addition to the original recommendation system, we added a relevance prediction system before we show the pins to a user, and we call it pinability. And what it does is simply to try to assign a relevance score to every single user pin interaction pair for total order ranking. And these are by linear models. And we have launched a total of 2 versions of these linear models, namely logistic regression and linear SVM rank. And we train all with open source software. So for example, we use scikit-learn for logistic regression and Sophia ML for SVM rank. And in our initial linear model, like the first version of linear model, we only had a very small number of features, like 12 features, such as the recent click-through rate of this particular pin, or whether the user has visited the board where the pin appears before, etc. So very simple model. And at the end of the lifespan of the linear models in Pinterest, in 2015, the last linear model actually has more than 500 dense features. So as you can see, even if we don't change the model itself, we continuously add more and more impactful features, and that helped a lot with user engagement. So here is very concrete details on like the impact of moving from time-ordered home feed to the first 12-feature linear model in home feed. So we were able to increase our daily active repeaters by 20% in home feed. So that was a huge number. And actually, as a matter of fact, it is still the biggest gains we have ever had within Pinterest from a single project, even up to today. So we were very happy and encouraged by these results. That's why we decided to continuously invest in machine learning models to personalize our home feed for our users. Of course, linear models have certain drawbacks. For example, the linear models cannot really well utilize high-dimensional and complex features, and oftentimes the engineers have to manually create feature crosses to add some non-linearity into the model, and that is a time-consuming task. And also, we found that the user-only features such as age, country, are not useful at all in a linear model for ranking purposes, and this is a little bit hard to interpret. Let me try to elaborate a little bit. So, in our task, we are trying to rank a few thousands of different pins for a single user. Then if we use a linear model to make this prediction, these user-only features would contribute exactly the same amount in terms of score to a final ranking score. So that will not change the order of the ranking among these few thousand pins. So such user-only features will not be useful. But of course, if you use user-pin interaction features, those will be extremely useful even for a linear model as well. And due to these drawbacks, we spent time and effort in analyzing gradient boosted decision trees, and we launched our GPTD models in 2016. So such model consists of an ensemble of regression trees, and every single tree is generated sequentially, and every tree is trying to minimize the residual error made by the existing trees before that particular tree. And the final prediction is nothing more than basically a sum of all the predictions for the different trees. And here is an example, GPT model. So by the way, these slides are directly taken from the XGBoost website for reference. So in this example, the GPT model consists of two trees. And the prediction problem is trying to predict if a particular user likes to play computer games. And the feature vector is a very simple three-dimensional vector, consists of user age, user gender, and whether the user uses computer daily. So as you can see, after training, we have two trees. If the input is a little boy, the little boy would follow the tree branch, would fall into the leftmost leaf node of the left tree with a score of +2. So that's a prediction for the first tree. And the same user instance, like the little boy from the second tree, would end up with a score of +0.9 from the left leaf node. So the overall prediction of this model for this input user instance little boy is 2.9. Similarly, if the input is like a grandpa, the grandpa would score an overall score of -1.9 from these two trees, basically sum up the leaf node values for this particular user. So and if we do ranking, the model would say, okay, the little boy is more likely to play computer games than grandpa. So that's, I think, which makes sense. So that's a very simple illustration of a two-tree GPT model. So in reality, in our production GPT model, we use about 700 plus dense features, and we have 350 binary trees. So instead of two trees in the previous example, we have 350 trees. And these trees all have slightly different loss functions. So for example, the first 200 trees would focus on maximizing the engagement on repeats as action. And the next 100 trees would emphasize maximizing international user engagement. And the last 50 trees would optimize the fresh content. When I say different loss functions, I mean, when we optimize to generate these trees, we would have different weights on the loss made by the different instances. And the max depth of our trees is 7, and because we have a huge number of training instances, all these trees are actually full binary trees. We don't have incomplete trees here. And we use XGBoost to train our model. And the final effect is that we were able to improve home feed daily repeaters by 10%. And that was the biggest gain we ever had in last year. So all these great gains are coming from this ranking model changes so far. And of course, GPTD has pros and cons compared with a linear model. So let's look at the advantages first. First of all, GPT is a nonlinear model, and it can effectively explore high-dimensional feature space. You can imagine every single instance will go through this root to leaf node, and we are actively adding nonlinear constraint every time we the instance move down towards the leaf node. And also, GPT has a very high tolerance to single feature value errors. What I mean by here is that in our data set, it's more often very noisy, not very noisy, but we have some uncertainty in our data feature values. And how GPT uses its feature value is by comparing that value with a particular threshold in your internal node. And as long as the noise is not big enough to perturb the final comparison result of that threshold value, the final order score doesn't change at all. So it has relatively high tolerance to feature value noise. And also, GPT provides very reliable feature importance analysis. So when we do machine learning or recommendation systems, more often than not, we would really want to know what are the most important features. After I added 100 new features in a single batch, I want to understand where does this game coming from? Like, do I just need the top 10 features, or do I really need the 100 features together? So many models, even like including DNN, they would not answer this question very satisfactorily. But GPT, on the other hand, is very good in this. So for example, we can view the importance by counting how many times a particular feature appears in all these hundreds of different trees. And that is a very indication of how important a particular feature is. And in reality, we use something slightly different, slightly more complex than that, but it's very similar to get very similar performance. The drawbacks of GPT model is the model complexity increases exponentially with tree depth. This is nothing new, as like the number of tree nodes doubles every time we increase the tree depth. And GPT is unable to effectively utilize sparse features, and it is unable to generalize well with enumerical features, and such as user country and language. So due to time constraint, I won't be able to talk more about the last two drawback points, but we did have our ways to address and resolve such issues. So if you're interested, feel free to talk with me offline. Okay, so moving to this year, we switched to TensorFlow-based deep neural network model for our home feed recommendation. And due to a few facts, like for example, like GPT limitations on utilizing complex features and crossing interactions. And also many pin user interaction features had to be defined explicitly within GPT. But in DNN, a lot of feature engineering is taken care by like how you define your feed-forward network. And also we heard stories about good things about DNN in computer vision and recommendation systems that prompt us to invest in this model moving change. So in our launched DNN models, we use very standard feed-forward neural network with 500 dense input features. And for every single, for all the categorical features, we apply an embedding layer to map it to a small vector of numerical values. And for all the other numerical features, we use a normalization layer to make it more standardized. And we have a total of 4 fully connected layers, and with hundreds of neurons in each layer. So during training, we apply a 10% random dropout of the hidden units, and we use a ReLU activation function and sigma get units, also used in the neurons. We use the standard weighted cross-entropy loss function, and the weight is by our definition of what is the most important action. For example, repeat would have a higher importance value than click-throughs, and then close-up, etc. And we use TensorFlow plus Keras for training with a single AWS machine with multiple GPUs. And the effect was that we were able to increase home feed daily active repeaters by 4% this year. So here's a closer look at our network. As you can see, like the bottom layer is a raw input layer where we have some like category features such as user country and pin country, and that goes through an embedding layer of a small vector length. And the right part of the first layer are those numerical features that will go through a normalization layer, just single neuron. And after that, we put all this input feature into 4 layers of fully connected neurons, and the final output is just one single number. That is our indication of whether the level of engagement that the user will get for this particular pin. And we use the final output number as our ranking criterion. And a little bit more about the hidden layer, hidden unit we use. The left-hand side is a standard ReLU activation function, and we added something slightly more complex, basically using a sigmoid. And the effect is that the model has a freedom to decide what information to pass and what information to not pass to the next layer. And this idea is very similar to the LSTM network, and we apply in all our hidden units. So I want to briefly compare DNN with GPTT because from as far as I know, these two models are the most popular ones used in industry by companies in Silicon Valley. And we have gone through the iterations of both of these. So DNN has its advantages, such as it has a larger model capacity. In our case, the DNN has about 1 million parameters versus GPTT of about 130K. And also, DNN is able to model more complex feature interactions through these fully connected layers or the ReLU sigmoid or gate function. And GPTT has this parent-child interaction path that models nonlinearity. And of course, DNN has some disadvantages from our experiments. So for example, like DNN requires a higher input data quality, and feature importance ranking, as I mentioned, is not as clear because it's more like a black box. And training process takes more time and time-consuming, as a matter of fact. Okay, lastly, if we take a step back, and we can see like during the 3 model evolution stages, we were able to increase the home feed user engagement by 40% over the past few years. But at the same time, if I sum over all the new features that we added, that engagement improvement was more than what we were able to do with the models. So does that mean like features are more important than modeling? I don't think so. Like it's because basically I think they are all very important. And if I can talk a little bit about the feature engineering experiences I had, we can see that the features are highly specialized. The useful features in one product or in one company may not work in another. And even like within the different products and Pinterest, our feature set actually quite significantly different. And also model work, feature work has a high chance of failure. A lot of our experimental features never made their way into a final production model, so we have to make the iteration on feature engineering really fast. And also feature work has a low transparency. When we talk with our colleagues in other internet companies, we can freely talk about what models we have been using and like what are the latest trend of improvement. But seldom did anyone tell you what are the most important features, most impactful features that we have in our models. And I think New York City has an extreme case here that so features are equivalent to the alpha signals we hear from the hedge funds, and no one talks about what they use to do their predictions. So that means like we need to grow our internal experts on that, and also lots of labor-intensive work and high return from effective features. Okay, so I want to mention that over the years, like a lot of people have significantly contributed to the home feed ranking problem, and we just want to acknowledge that, and we have some engineering blog on top of that. Okay, any questions? I think I have less than 1 minute, but thank you. Sure.
So in the GPTT model, you had 700 dense features, and in the DNN model, you started out with 500.
Yes.
So,
all right.
yeah.
So that's a very good question. As I mentioned, like DNN is very good at feature crossings and also find the complex feature interactions. What we find is that we can remove a large portion of the features used in GPTT and still achieve the same level of performance in DNN. So that's why we remove those. Okay. I'm question offline in that case.
Yeah, he'll be around right before the lunch break.